Hello everyone. So today we're going to go over section 10.4, logarithmic and exponential equations. Suppose we have the following conditions, that the base c and then the arguments L and R are all greater than 0, and that c is not equal to 1. So then what we'll have is the following, and that is, if log base c of L is equal to log base c of R, then L is equal to R. Now, likewise, if L is equal to R, then we can take the logarithm of both sides in some base c, and so log base c of L is equal to log base c of R. Okay, so the first type of question that we are going to be dealing with are logarithmic equations. So let's look at example number 1. We have 2 log x is equal to log 16. The first thing we should do here is to consider the restrictions, and that is x must be greater than 0. Since x is an argument of a logarithm, it has to be positive. So with this equation, what we can do is to move the 2 to be the exponent, x squared, on x squared, sorry. And so we have log x squared is equal to log 16 on the right-hand side. From what we saw in the box above, we know that since log x squared is equal to log 16, then x squared must be equal to 16. So x must be equal to positive or negative 4. However, we need to reject negative 4 since it's less than 0. So then we have the final answer, x is equal to 4. And that's it. So with the next example, we have 2 separate restrictions that could be combined. First one is that x plus 4 must be greater than 0. So therefore, x is greater than negative 4. And then in the second set of parentheses, we know that x plus 3 must also be greater than 0. And therefore, x is greater than negative 3. So any number that is greater than negative 3 is always greater than negative 4. However, the opposite is not true. So the combined restriction from these two parts is that x is greater than negative 3. Okay. Next, we can now consider the equation itself. So first thing we can do is to move log base 6 of x plus 3 to the left-hand side of the equation. So we have log base 6 of x plus 4 plus log base 6 of x plus 3, and that's going to be equal to 1 on the right-hand side. Okay, so here we have the sum of 2 logarithms, which means we can multiply together the arguments. So we have log base 6 of x plus 4 times x plus 3. Now, the right-hand side we can also write as a logarithm with base 6. So this is log base 6 of 6. So from there, we can rewrite this as just x plus 4 times x plus 3, and it's equal to 6 on the right-hand side. We can now multiply the 2 binomials together to give us x squared plus 7x plus 12 is equal to 6 on the right-hand side. Okay, so this is just a quadratic equation at this point. We can move the 6 to the left-hand side. We have x squared plus 7x plus 6 equals 0, which can then be factored. We have then x plus 6 times x plus 1 is equal to 0, which means that x is either equal to negative 6 or negative 1. Now, based on our restriction, the -6 answer will then be rejected. And so we're just left with x equals to -1. Okay, so next we're going to look at exponential equations that we wouldn't have been able to solve before because in the previous unit we used common bases to solve exponential equations, and here these equations will not necessarily have common bases. So let's look at example 2a. We have 4 to the power x equals 12. So what we can do here is we can take the logarithm of both sides. So we have log 4 to the x is equal to log 12 on the right-hand side. Now, using the power rule for logarithm, we can move the x in front of the logarithm on the left-hand side. So we have x log 4 is equal to log 12. From there, we can simply divide both sides by log 4, since it is just a number. And we have log 12 divided by log 4 is equal to x. Like so. From there, we can use a calculator to evaluate this number, and we get an approximate value of 1.792. Okay. Let's look at another example. Example B. So here, very similar. We can first move the 4 to the right-hand side. So we have 8 to the x is equal to 40 minus 4, which is, of course, 36. We can then take the logarithm of both sides, just like in example A. So log 8 to the x power is equal to log 36. From there, once again, we use the power law to move the x. And finally, we divide the two logarithms to isolate x by itself. So x is going to be equal to log 36 divided by log 8. Oops, sorry about that. And we'll get an answer, 1.723. So just as it says right here, the two ways that we need to express the solution is as an exact value in the form of a quotient of two logarithms, or to 3 decimal places using a calculator. So here we have both, just as in example A. Okay, so let's move on to the more challenging examples, C and D. So notice that in example C and example D, we have the variable as the exponent on both sides of the equation, so it's a little bit more challenging. So let's look at the first of these. Here we can simply take the logarithm of both sides and also move the, sorry about that, move the exponent to be a coefficient in front of the logarithm. So we have 3x log 6 on the left-hand side, and then 2x minus 1 log 3 on the right-hand side. And the goal here is to isolate the x by itself. So on the left-hand side, we can rewrite this as x log 6 cubed. So we can just move the 3 back to be an exponent, but leave the x in front of the logarithm. And on the right-hand side, we will distribute. So we have 2x log 3 minus log 3, just like so. And from here, what we can do is evaluate 6 cubed on the left-hand side. So 6 cubed, of course, is 216. And on the right-hand side, we can move the 2 to be the exponent on the 3, so 3 squared is what we have, then minus log 3 still. Okay. So from here, we can then evaluate the power. 3 squared is 9. So we have on the right-hand side x log 9 minus log 3. Here then we can move the x log 9 to the left-hand side of the equation. So we have something that looks like this. X log 216 minus x log 9 is equal to negative log 3. So notice that the two terms on the left-hand side have a common factor of x, so we can factor that out. We have x, and then in parentheses, log 216 minus log 9, and that's equal to negative log 3. Okay, so we have a difference of logarithm, which means we can divide the argument. 216 divided by 9 is 24. So we can rewrite the left-hand side as x log 24, and that's equal to negative log 3. So what that means, of course, is that x is just equal to negative log 3 over log 24. Alternatively, the negative log 3 can be rewritten as log 1/3, since that is negative 1 in front of the logarithm. So if we were to move it back to being an exponent, we have 3 to the negative 1 power, which means we have log 1/3, and that's going to be still over log 24 on the right-hand side, sorry, on the denominator side. And now finally we can divide these two using a calculator, and we'll get negative 0.346 to 3 decimal places. Okay, so the questions are quite involved, but if we take it step by step, they are workable. So let's look at another one. Example D. So here, notice that we have a coefficient in front of our power, this 2 right here. So we can take still the logarithm of both sides. So we have log 2 times 3 to the power of x minus 2 is equal to log 7x. So the left-hand side, the argument is a product of two terms. We can then rewrite it as the sum of logarithms. So we have log 2 plus log 3 to the x minus 2. And the right-hand side, we have log 7x. So from here, of course, we can use the power rule. So we have log base 2, and then x minus 2 log 3. And that's going to be equal to x log 7. From here, once again, we can apply the distributive property. So that will give us log 2 plus x log 3 minus 2 log 3 is equal to x log 7. And from here, we can move the terms with x's to the right-hand side of the equation and simplify it a little bit. So we have log 2 minus log 3 squared, which is 9. And that's going to be equal to x log 7 minus x log 3. So on the left-hand side, we have a difference of logarithm, which means we can divide the argument. So the left-hand side simplifies to log 2 over 9. And the right-hand side, we can factor out x and then also divide the argument. So that will be x log 7 over 3. And so finally, if we were to isolate x by itself, we would have x is equal to the quotient log 2 over 9 divided by log 7 over 3. So again, just like before, we still want our answer as a quotient of two logarithms, which is what we have, and then afterwards using a calculator to find an approximate value for it, and that will be negative 1.775. Okay. So let's look at one more example. Again, there's two here, but we'll just go over E, as that will be quite sufficient, I believe. So once again, we can take the logarithm of both sides to start. So we have x plus 2 log 3 is equal to 2x, sorry about that, in parentheses, 2x minus 3 log 5. So two things happen here. Number one, we take the logarithm of both sides, and then using the power law of logarithms, we move the x plus 2 to the front of the logarithm on the left-hand side, and 2x minus 3 to the front of the logarithm on the right-hand side. Now we apply the distributive property. We have x log 3 plus 2 log 3 on the left, and on the right-hand side, we have 2x log 5 minus 3 log 5 on the right. So any coefficient in front of logarithms will rewrite as exponents. So that means we have x log 3 is equal to log 3 squared, which is 9, of course. And on the right-hand side, we can move just to 2 and leave the x. And then we have log 5 squared, which is 25. And then minus log 5 cubed, which is 125. From there, we simply move all the terms containing x to one side of the equation and move out x to the other. So we can write this as, for example, log 9 plus log 125 on the left-hand side. And on the right-hand side of the equation, we have x log 25 minus x log 3. Okay. So on the left-hand side, we have a sum of logarithms, which means we can multiply together the arguments. 9 times 125 is 1125. Whereas the right-hand side, we can factor out the x, and that will leave us with, in parentheses, log 25 minus log 3, which means we can divide those two arguments. We have 25 over 3. Just like that. And finally, if we were to write this in terms of just x, then we have x is equal to, let's see here, log 1125 over log 25 over 3. And then from here, we can once again use a calculator, evaluate this, and we'll get an approximate value of 3.314. And that's it. Okay, so the next piece is to look at some word problems involving exponential growth and decay. So in the last unit, we've also looked at these questions, but it was mentioned that when we were solving for time, it was quite difficult. We usually had to use some trial and error. But now with logarithms, we can find time more precisely. So let's look at the first example. It says that Canada's population has a growth rate of 1%. Canada's population in 2001 was approximately 30 million. We're going to estimate which year the Canadian population will reach 50 million. So we have here then on the first step, we have population P is equal to P naught, the initial population, and then 1 plus R, the growth rate, to the n power, whereas n is the number of years that passed since 2001. So the population we're looking at is 50 million, so we can simplify that as 50. The initial population in 2001 was 30 million, so just 30 here. The growth rate is 1%, so 0.01, and then to the n power. So if we were to simplify this expression, we can divide both sides by 30. So we have 5 over 3 on the left-hand side. And the right-hand side, 1 plus 0.01, of course, is 1.01 to the n power. So now what we can do is to take the logarithm of both sides. So we have log 5 over 3 on the left-hand side. And that's going to be equal to n log 1.01. Since we can use the power law for logarithm to move the exponent n in front of the logarithm as a coefficient, So now we can divide both sides by log 1.01, so n is going to be equal to log 5 over 3 I guess it's not quite a coefficient, and because it is a variable, but it will be in front of logarithm. That's the idea. So here we have n is equal to, once again, log 5 over 3 divided by log 1.01. And that could be evaluated on a calculator, which gives an approximate value of 51.3, and time is in years. So the year will be 2052. That's our answer. Okay. So next question, very similar, slightly different setting, of course. We are looking at an investment and how long will it take to grow by $400 starting at $1,000. 6% annual interest, compounded monthly. So the investment's worth, so we'll just call it I, is equal to I naught, the initial amount that's in the account, multiplied by 1 plus R over n, where n is the number of compounding periods per year, to the n times t. So here we're looking for $1,400. We started with $1,000. The rate is 6% compounded monthly, so divide by 12, and then to the 12 t power. We can divide both sides by 1,000, so 1.4 on the left-hand side. And then on the right-hand side, 0.06 divided by 12 plus 1 is 1.005. And this is, of course, still to the 12t power. From here, we can take the logarithm of both sides, just as we did with the previous example. So log 1.4 is equal to 12t. Actually, we don't even have to do that. We can rewrite this as t, and then log 1.005 to the 12th power. So we took the logarithm of both sides and then used the power law only on the variable t to move it in front of the logarithm. Then we can isolate t by itself. T is going to be equal to log 1.4 divided by log 1.005 to the 12th power. And that could also be evaluated on a calculator as well, and we'll get an approximate value of 5.6 years. Okay. which of course can be converted into years and months, but 5.6 years is quite sufficient for our purposes here. Okay, so let's look at one final example here. Radioactive isotope, half-life of 45 minutes, so let's set it up with amount remaining is equal to the initial amount. This is a half-life question, so our base will be 1/2, and t over 45, since the half-life is 45 minutes. So the amount will be 15 at the end. It started with 480, and we have 1/2, again, to the t over 45 power. Now, 15 divided by 480 is 0.03125, and that's going to be equal to, on the right-hand side, 1/2 to the t over 45. So as before, we can take the logarithm of both sides, so log 0.03125 is equal to, let's see here, we can write this as t over 45, and then logarithm of 1/2. So once we rearrange everything, t is going to be equal to 45 times log 0.03125. Notice that the first step to isolating t would be to multiply both sides by 45, so the 45 would end up in the numerator. And this will be divided by log 1/2 to get t by itself, and we'll get 225 minutes. So a nice whole number for an answer there. So today we've looked at solving a couple of logarithmic equations, for example number 1, followed by exponential equations where the bases are not the same on the two sides of the equation in example 2, and then we finally followed up with some exponential growth and decay problems in examples 3, 4, and 5. And that's it for today, so once again, thank you for listening.